Hello, everyone. Let me share the screen.
It's a bit faint, at least on my end, so maybe
Can you hear me now?
could be better. I mean, it's just borderline, I would say.
Okay. Second. Settings.
It is still very, very faint.
Yes.
So I'm not sure if there's something wrong with your video headset or with your headset.
Yeah. What about now?
Much better. I think that is acceptable for for starting the meeting and continuing the session.
Okay. Well, hello, everyone. My name is Andrei Alexeyenko. I'm a core developer of the GROMACS molecular dynamics package at KTH Royal Institute of Technology and Science for Life Laboratory in Stockholm. And today I will talk about our experiences adding one API support to GROMACS. So first, let's talk about our code base. GROMACS is an open source GPL licensed molecular dynamics engine. It's very widely used. By some estimates, GROMACS is accountable for around 5% of the supercomputer usage worldwide. And we are not limited to supercomputers. GROMACS is being run as part of the Folding at Home projects on laptops. And it's used for modeling of a very wide range of biomolecular systems. It might be some small individual proteins, or it might be a big system of some ion channel embedded in a membrane. And GROMACS is not only supports wide range of say x86 hardware, but it is actually run on different architectures. And it's not that we theoretically support them, it's portability in practice. We are actually testing on all this hardware and with all those different distributions and different accelerators. So we support, besides x86, we'll support ARM, Power, we support multiple SIMD backends, and we support all three major vendors of GPUs for offloading some of the operations. And GROMACS is included as part of many Linux distributions, and as well it's tested to work reasonably well on Windows and Mac, although Linux is our primary target. In GROMACS 2020, the latest release, which it's not yet released, it's gonna be released later this week or maybe next week, but as you can understand, it's pretty close to it. It's almost 500,000 lines of C++ code. And while we try to be modern, follow the best C++ 17 guidelines, the code has around 30 years of history, so it's a huge code base, and it has a bit of legacy, a bit of idiosyncrasies. So that is something to keep in mind when doing any work on the code and when discussing these results. So I will be describing our experience, but if you're interested in porting some new code or starting from scratch, some of the things might not be applicable. So keep that in mind, please. And GROMACS already uses multiple levels of parallelism. It uses MPI for communicating between multiple nodes in the cluster. Within a single node, it uses OpenMP to distribute the load between different cores of the CPU. There are SIMD intrinsics for compute-intensive parts of the CPU code, and as I guess most modern molecular dynamics code, we support GPU offload. Molecular dynamics was one of, I guess, of the first scientific workloads that got that started to heavily use GPUs, and yeah. Right now, most of the popular packages do support some form of offloading. And the GROMACS, we actually support 3 different frameworks for GPU offload. It is CUDA, OpenCL, and since recently, SYCL. First, let's briefly describe what exactly is the problem we are solving. What's the structure of the code, or at least the most computation-intensive part of it. So molecular dynamics is an iterative problem similar in many ways to the widely used as a testing tool, as a learning exercise, n-body problem. You have multiple points in a 3-dimensional space that somehow interact, and you want to compute how they move as time progresses under the given forces. Except it's not just gravity, it's not gravity. It's different force like electrostatics, covalent interactions, and so on. But the general formulation of the problem is quite similar to classical n-body. And the typical time step, so the simulated length of single iteration, is 1 femtosecond or a few femtoseconds. But the biologically interesting processes happen on a scale of microseconds to milliseconds, or sometimes even to seconds. So we need to do a lot of different steps. And yeah, each step is very similar. We probably do some balancing and pair search to optimize the non-bonded interactions. Then we compute all the different forces, shown as colorful rectangles here. Then we reduce those forces to get the total force acting on each particle. We integrate the equations of motion, rinse and repeat many, many times. And when parallelizing such code, we need to balance different, sometimes competing concerns. First, latency. We need to do this loop many, many, many times per second. So quickly dispatching job, quickly complete individual tasks is paramount. We want to balance the load between CPU and GPU to avoid any of them stalling without work, because if it's stalling, it probably could have been doing something useful and could have been making our code run even faster. And another concern is that we are a relatively small team, and we need to prioritize exactly which parts get ported and which features are being used. So we cannot really port everything, every single possible code path, every single possible force calculation to GPU. And additionally, of course, while we want to minimize latency and balance the load between CPUs and GPUs, exchanging data all too often between CPU and GPU is costly. We want to balance the load and probably scale our simulations to many, many nodes in an HPC cluster. But of course, internet communications is even costlier in terms of latency, in terms of slowdown. And furthermore, complicating all this further, not only do we need to balance all these competing concerns, we also need to make sure that we can achieve optimal performance on a wide range of simulated systems, from small proteins, maybe thousands of items, to hundreds of thousands of items. And we also want to run on different hardware. As I said, we are running GROMACS as part of folding at home on laptops, maybe with integrated graphics or without any usable GPU, or it can be run on near exascale machines that we are targeting in the near future when we get access to them. So as a result, that translates that real MD loop is much more complex than a simple picture I have shown a few slides back. Because we have loads split between CPUs and GPUs, we have multiple data transfers. And what's more, we have to, this schedule is not static. So some data transfers occur only conditionally. Sometimes we can balance the work between CPU and GPU by changing parameters. We can reduce the frequency of certain updates by increasing the length of different tasks. And we also need to keep in mind that some tasks that are involving communications with other ranks in multi-node simulations are higher priority because we do not want to stall other ranks in our simulations. So there are many possible tuning knobs that either user can set or we set in runtime as a part of auto-tuning. And besides, not only can we change the parameters of each of those blocks shown here, we can actually move those blocks between CPU and GPU and possibly between ranks. So here shown is a schedule that does PME computation on a CPU, but we also support PME computation on GPU. Similarly, integration for our CUDA and SQL port. Integration can be done on either CPU or GPU. And it's dependent on the specific load and, for example, what forces are being used, because if all the forces used in simulation are offloaded to GPU, it's often preferable to also port integration to GPU so that the whole core MD loop can be completely scheduled to GPU without any synchronization on every iteration. But if there are any forces that are CPU only, then moving integrations to GPU might actually be slower. So, and we need to support all those different workloads, which adds quite a lot of complexity to our scheduling code. So when the SQL porting project started in September 2020, GROMACS only supported NVIDIA, CUDA, and OpenCL. So NVIDIA was the oldest and much more developed framework. So it had most features ported to GPU, but obviously this being CUDA, it could only support NVIDIA hardware. Now, NVIDIA for a long time has been market leader, so it was acceptable for most of our users. But we also supported OpenCL to target AMD and Intel hardware. It was much less developed. As you can see, much less features were supported on GPU with OpenCL, but it was very useful because it allowed us testing on more hardware, supporting more hardware. And as I said, GROMACS prides itself in being portable in theory and in practice as well. And okay, you might think we already have well-developed NVIDIA, and currently most of the computing clusters are, let's be honest, using NVIDIA GPUs. We have OpenCL for portability. Why bother with SQL? Why bother reading another framework? So first is that new machines are coming. New exascale clusters are hopefully be deployed soon. They were planned for 2021. Due to pandemic, it all got delayed. But yeah, hopefully there will be available to users soon. And those clusters are not NVIDIA. They use AMD and Intel GPUs. So we do need to put more efforts into supporting those kinds of hardware. It's no more NVIDIA world. And furthermore, OpenCL, while it offers us a portability layer, while it can be used to run on different architectures, and in terms of hardware support, at the moment, it's probably even better than SQL, because it also supports different embedded hardware, which is nice, but for us not very relevant. But OpenCL, at least the widely supported subset of it, and especially at in the middle of 2020, when this decision was made, was only C99. The C++ was standardized, but was not widely supported by GPU vendors. And the rest of the GROMACS was already C++ 17. So we had still some parts in legacy C++, but it was mostly modern C++ 17. So having a mix of C99 kernels and C++ in the rest of code was a maintainability burden. We had to duplicate some functions, we had to duplicate some structure definitions. Also, OpenCL uses separate source model, which is not ideal for deployment. Again, it's not very developer friendly, I would say. So OpenCL is okay-ish, but it's hard to maintain, so it's not an ideal solution, especially long-term. So here comes SQL. So it's why did we decide to settle on SQL as a new GPU framework in GROMACS? So first, it's open standard. It's not tied. It's not another proprietary thing. So it's vendor neutral, and there are open implementations that give a lot of credibility to this standard as a long-term solution. Another good point for us is that SQL doesn't try to reinvent the wheel. Both one API and the other implementation we were considering at the time, KeepSQL, are based on top of the existing backends, which means that they are more stable than some completely new thing. So at least low-level device compilers are well established and tested. And also a big benefit is that we could use existing profiling and debugging tools. And Intel offers a great set of tools for their GPUs, but if we want to use SQL as a compatibility layer, we want to also be able to debug it and profile it on NVIDIA and AMD hardware. And being able to just use native tools is very, very nice for that. Besides, SQL is uses standard C++ syntax, so we don't need to any special code formatting tools, any special linters, and all that. So it's plain C++, and most of the tools, helping tools that we use to aid development, they already supported. And logically, the SQL API is very similar to the way OpenCL is organized. So since we already had OpenCL support in our code, that reduced the required effort. So a bit more on that. If we compare, to summarize it, if we compare all the frameworks, SQL has benefits that, like OpenCL, it is open standard. It has support for hardware by all three major GPU vendors. It's a single source model with modern syntax, unlike OpenCL, it is widely supported subset of OpenCL. So SYCL looks like a nice way to, as a future compatibility layer in GROMACS. We are not removing OpenCL at the moment, although it is deprecated and most of the current development effort are directed into expanding SYCL support rather than porting more features to OpenCL. But OpenCL currently is still there because it has existed. It's much more tested in terms of both existing implementations, existing backends, and in terms of its supporting GROMACS. So, having decided to do the SYCL porting, we had to make a plan for it. The initial goal was to use one API DPC++ and target Intel GPUs, but since we aimed to keep GROMACS portable, we were conscious to stay as standard compliant as we could without compromising other concerns, and not to use too much of the vendor-specific extensions, if that can be helped. So first things was to prepare at least somewhat the code base for ingestion of yet another chunk of code. Then, of course, setting the priorities, first port the most time-consuming kernels that usually account for vast majority of the runtime, the non-bonded kernels, and then port other forces and the update kernels so we can achieve the GPU resident loop, which is a nice thing for end users performance-wise, and besides it is nice thing in terms of testing and validating how well the SYCL runtime performs. Another thing we considered when starting SYCL porting is DPC++ compatibility tool. So it's a program to automatically or semi-automatically convert your existing CUDA code to one API DPC++ code. And yeah, so we had CUDA code. It seemed like a viable approach, but upon examination, the biggest problem was not really just rewriting the code. It was nicely integrating the code into the whole code base, making a nice, logical, performant abstraction layer so we can have all three GPU backends, CUDA, OpenCL, and SYCL, together without too much code duplication. And yeah, besides, while we did support Intel with OpenCL, CUDA kernels were, as one might expect, optimized for NVIDIA GPUs. And yeah, there were quite a lot of optimization specific to even individual generations, individual architectures. So porting NVIDIA kernels and expecting them to run nicely on Intel, I mean, they would likely run, but they won't be performant. We already had optimized kernels in our OpenCL, so converting CUDA kernels was not, in many cases, reasonable. And after considering all the things, we decided that manual porting without the use of DPC++ compatibility tool is the way to go. The tool can be nice, can help porting simple kernels, which don't have much GPU-specific optimizations. But in this case, manually rewriting this kernel is also not a huge undertaking. And for GROMACS, which already had multi-vendor support via OpenCL, it was more crucial to get actually nice and maintainable code rather than to get it weekly running, to get some hacky implementation that okay that runs but is not long-term supportable. For a SQL version, we already had optimized kernels that relied on some features that were not part of SQL 1.2 standard. They were like subgroup level shuffles, they were floating point atomics. And in mid-2020, when we started porting GROMACS to SQL, yeah, they were just vendor extensions. And while we did want to avoid using those and relying on those, we had to be practical. And one API was our main goal, so we decided to look at the draft of SQL 2020 to try to stay within it, try to stay more or less, when possible, compliant with the current SQL 1.2, but when needed, when it couldn't be helped, we used one API extensions. But yeah, as much from later, most of what we used was planned for inclusion and actually became a part of the upcoming SQL 2020. So yeah, it was an easy compromise to make. So we stayed not within the standard as published, but within the draft of the next standard, which turned out to be good enough for our portability. And in terms of GPU framework structure and API, not talking that much about kernels, but rather about the host glue code, which was for us most of the work and most of the effort, most time-consuming part, because we wanted again to make it nice and maintainable and have a single abstraction layer on top of all three backends. So CUDA, which we had as a first GPU layer in GROMACS, is built around in-order queues. It does have, in the recent versions, explicit DAG, called CUDA graph, but we are not using it in GROMACS, although it's being researched as a possible future feature, but it's not used now. CUDA uses separate events, separate tasks that are enqueued and that can act as synchronization points, and timing measurements are performed between those pseudo tasks. There are other, for us, relatively minor concerns about how device management is organized, the native sizes of the size of some native types, the resource management, how actually queues are configured. But that's relatively isolated things. The scheduling and synchronization and timings are most important. Now OpenCL also supports in-order queues. It also supports out-of-order queues, but we were not relying on them in GROMACS. Again, OpenCL for synchronization supports both task-associated events, like we have in SQL, where you submit a work into the queue and you get an event which you can use later to synchronize with the completion of this task. Or you can insert a barrier, like in CUDA, which is a separate thing that lives in in-order queues and will get triggered whenever all the previously submitted work completes. Timing measurements in OpenCL is done on single events. You cannot measure a time between those two barriers like you do in CUDA. And yeah, say float 3 is 16 bytes. It has padding, while in CUDA it has not. There is different approach to device and queue management. And SQL inherited most of those things in terms of all those device management minutiae. But in SQL 1.2 standard, in-order queues were not a thing. Only implicit DAG using buffers was fully supported. And even in SQL 2020, there is no way to insert, no standard compliant way to insert a barrier. So you can only synchronize with individual tasks. Now, luckily, for quite some time, we already had an abstraction layer over CUDA and OpenCL. And since a lot of things in SQL are similar to OpenCL, dealing with some of those discrepancies was trivial. Because we already had the code, we just had to rewrite the same logic we used, say, for device selection and detection on OpenCL in SQL. But the scheduling and synchronization, that was a bit more complex, again, given our self-imposed, partially constraint of trying to stay within the standard. And besides, implicit DAG, data dependency-based scheduling approach, in general, it looks pretty enticing. So let's dig deeper into the scheduling part of things. So in theory, DAG should be more powerful than in-order queues, because you would not accidentally miss synchronization. You have buffers, you have accessors that set dependencies between different tasks. It can automatically schedule workloads in parallel that don't conflict in terms of data access. So it sounds really good. So it's safer, it can be more performant. And for many applications, that is a huge benefit of using DAG. Unfortunately, in GROMACS, we already put a lot of effort into working with in-order queues. We already have all the synchronizations, and it's mostly well tested. We do occasionally encounter some synchronization bugs. We are not completely free of them, but yeah, it's well tested and it's well optimized. We already use multiple queues. We already run workloads that we can in parallel. So actually, the benefits of DAG are not that important for GROMACS. And since we already do synchronizations manually, we risk of incurring extra loss by synchronizing twice, because first it's DAG doing some, introducing some inter-device dependency, and then we are also manually synchronizing, so it's not great. And also, since we were relying on barrier synchronizations, it introduced the problem of implicit dependencies. So for example, if you submit two device-to-host copies into an in-order queue, and then enqueue a barrier, and then wait for the barrier, you can be sure that both tasks are complete. Now with DAG, if you submit a copy to a host memory, not to a buffer-based memory, but to some external mallocked buffer, and then only synchronize with one of them, and wait for this event, then you cannot be sure that the first one is complete. And since we have a very complicated schedule which can take many different paths depending on which features are used and which features are offloaded to GPU, we unfortunately do sometimes have such implicit dependencies. Probably we should work on improving our code. We have some efforts in that direction, but unfortunately, in the current state, we have such implicit dependencies. So just using the last event from a chain of operations, like we implicitly do with barriers, is not feasible. It will lead to data races, which is not nice. And besides, DAG places a huge demands on the runtime, because, for example, going back to our schedule, we have this shown in red, the hot path we need to receive and send back the data to the neighboring MPI ranks as soon as possible. So we want to make sure that non-local, non-bounded forces are computed as fast as possible. And with SQL, there are no priorities, no way to indicate to the runtime that this kernel is more important. You need to run it ASAP, while this other kernel can probably wait. It's not as critical. So there are no mechanisms in SQL to indicate such things to the to the runtime. And again, the balancing of work, the parallelizing of different workloads automatically based on data dependencies may be nice for new codes, but we already had manually parallelized schedule. We already put a lot of effort into splitting the work between different in order queues. So now we were just trying to, okay, we have this done manually, but let's throw away all this work and hope that the runtime will do better. And early experiments show that it does not. And besides, since we want to have 3 different GPU backends supported at the same time, using in-order queues in one case and DAG for SQL is not maintainable long term. We want to have the code between backends as uniform as possible, because we have limited resources. We cannot support completely different scheduling code for SQL and CUDA. So where does it leave us? So we don't want to rely too much on DAG scheduling, but in the late 2020 even, USM and in-order queues were not yet part of the standards, so we had to, as a compromise, use buffers as a simple device memory, and still do the explicit synchronizations between copies from host buffers to device, because for host we were using our own allocated arrays. So we don't use the implicit ability of SQL buffers to automatically copy data between host and device. Again, it's a nice feature if you're dealing with a new code, but if you already had all the explicit data transfers in place, and sometimes you initiate data transfers early on, so you have data ready when it's needed, it doesn't really make much sense to stop doing that and just rely on runtime and hope that it does the right thing. Now with buffers, we could still use the synchronizations between different device tasks. For example, between different in order, what we did in CUDA between tasks in different in order queues. But in our early experiments, removing those implicit synchronizations and just relying on the abilities of the runtime to set up the dependencies properly didn't offer any performance benefits. It was working fine, but it wasn't really getting us any better iterations per second than we were getting with explicit synchronization set up manually. And now in 2021, when we had final draft of SQL 2020 and it was fully supported, well, not fully, but to a larger degree supported, we switched to the USM and in-order queues to be more consistent between different backends and minimize the overhead. we're still keeping buffers as an option, so you can still compile GROMACS and force it to use SQL buffers as underlying storage. So because we still are interested in exploring what tag scheduling can do, but it's not the main approach. And another thing that forced us to switch to USM is that in some cases, using accessors in complicated, complex kernels led to underwhelming performance by the compiler optimizer. Accessors are complex data structures, and yeah, compiler needs to do very well to optimize them out. While USM, it's just a single pointer. You don't have to try to strip out extra member fields or anything from that. So yeah, we went initially into emulating in-order queues, so to say, with DAG. Then we went straight to using in-order queues across all the backends. Now with the synchronization, it was a bit more complicated. As CUDA, at CUDA, we rely on creating the events once at the start of the program, and then reusing them. We enqueue them, then wait for them, then enqueue them again. Sometimes we, for example, may pass an event to the constructor of some force calculation function, and later it will wait for this event to make sure the data is complete. So events are used before the corresponding operation are being even enqueued. And yeah, it's better synchronizations, and often it's used very, very far from the place where actual work is enqueued. For example, we might have some conditional code that submits one force calculation, then another force calculation, and upper on the call stack, we just submit the barrier and say, okay, but whichever work was submitted before, one kernel, two kernels, data copies, we just wait for them all. So even in addition to the issue with implicit dependencies between two workloads, there's also the case, there's also the issue that often we cannot just even simply get the event associated with the most recently submitted kernel easily. Yeah, technically it can be done, but it will require sometimes significant rework because the event can come from one place, from the other. You need to add to change the function signatures to propagate this event up the stack. So it's not easy. And yeah, to resolve it, we had to rely on one API specific extension that does exactly what CUDA barrier does. It enqueues a barrier point into a queue that just waits for all previous submitted work. So yeah, it was not ideal for us because it was not part of SQL 1.2, and it was not going to be included in SQL 2020. But it was the only way to get things working without significant rewrite of the code. And while it was not standardized in other implementations, after some discussion with HipSQL team, it was also possible to persuade them to add a similar extensions to their runtime. So while it's not standard, such things are supported in at least two existing SQL implementations. So it's not too bad. So yeah, summarize, a lot of differences between SQL and CUDA can be now as of SQL 2020, and with some vendor-specific extensions can be resolved. and some others that are due to the whole slightly different philosophy, so to say, of the two frameworks, can be resolved a bit less ugly, less conveniently, but at least we already had a abstraction layer in place that somewhat abstracted those differences away. Another thing to keep in mind is that SQL throws an exception when error happens, while CUDA and OpenCL do error codes. In SQL and OpenCL as well, but if you're only used to CUDA, that can be an issue. You have variable subgroup sizes. You can force compilation with STMD32, but on say laptop GPUs, it's usually it will be very slow. And another issue that is encountered when you're rewriting the kernels manually is that in CUDA and OpenCL, when an indexing thread in multi-dimensional grid, first index is the fastest changing, while in SQL it's the last one. So if you're relying on subgroup functionality and use multi-dimensional grid and you're porting the code from CUDA and OpenCL manually, that can be an issue. I guess I'll skip this once. And as I said, we wanted to be portable. We didn't want to lock GROMACS to only DPC++. That's why, I mean, as I said, we are not having one API backend, we are having SQL backend in GROMACS. And with our goals of targeting new high-performance hardware, the second implementation of interest was HipSQL. So while initially the goal of the SQL porting in GROMACS was to support Intel GPUs via Intel One API, it was also interesting to see how it can be used to target different hardware through different implementation. And actually it turned out to be not too bad. We had to work around some backend issues, mostly related to incomplete implementation by SQL 2020 by, at the moment, either HipSQL or One API, or sometimes that it was implemented, but it was implemented as a vendor extension. And we had to work with the HipSQL team closely to develop an analog of the enqueue barrier extensions that exists in One API to enable the barrier centralization that we rely on. Porting to HipSQL helped us in uncovering some bugs because, for example, we were sometimes writing data to the read-only accessor, and it was working fine with One API, but it's obviously incorrect logically, and HipSQL was failing there, so it helped us to catch these bugs. But yeah, that's something that had to be fixed before we could use HipSQL. And yeah, we had to do some CMake infrastructure work to be able to detect both HipSQL and One API. And we already had optimized kernels for AMD in our OpenCL implementation, so that part was already covered. And as a result, with relatively little effort, we can use SQL backend to run on GPUs from all three major vendors. We can use Intel GPUs via One API DPC++. We can use AMD GPUs, or at least professional ones, via HipSQL. The support for consumer AMD GPUs is still only promised by AMD, but hopefully it will be available in the near future. And for CUDA, we can use either HipSQL or we can use the open source Intel LLVM, which is a basis of One API DPC++, which is developed collaboratively with CodePlay, and which is has nice and fully functional CUDA support. And HipSQL also was the main victim of accessors, because in complex One API was able to mostly optimize away all the accessor-related overhead, while in HipSQL we had huge spills until we switched to USM. And while still our complex kernels with SYCL are slower than corresponding HIP or OpenCL kernels. They are getting there. And for simple kernels, SYCL performs just as well and sometimes even better than OpenCL. But I think to keep in mind is that with HipSYCL, we are still seeing some runtime overhead, which again, we are working right now closely with the HipSYCL team to resolve. And all that was achieved with very little GPU-specific code. We had some vendor-specific optimizations, mostly related to subgroup level functionality. And we had to use different code paths for the FFT, because for Intel GPUs, we could use MKL, which interacts nicely with DPC++. And for AMD, we had to use RockFFT and the HipSYCL specific extension to achieve the interoperability between SYCL runtime and queues and native operations. And the same can be done with QFFT for NVIDIA GPUs, but it's not done yet. NVIDIA GPUs are not a priority for us on SYCL, so yeah, it's in our work plan, but not implemented yet. And another notes from our journey to enabling SYCL support in GROMACS is that, yeah, existing tools are great. It's a great benefit to be able to use different tools and different vendors. For example, using the compute sanitizer from NVIDIA helped us find a bug that was present in on all backends. So it was a logical bug in our kernel. It was affecting all Intel, AMD, and NVIDIA GPUs, but it was easiest to find out with with NVIDIA compute sanitizer, and it was only possible because we could use SYCL to target NVIDIA GPUs. Another issue is that sometimes compilation is slow, and sometimes in the beginning when we didn't use magic SYCL code split switch, the just-in-time compilation could take several minutes. So every time you started your code, your GPU program, it could take a few minutes to just compile all the flavors of different kernels. Since usually you use only one or two flavors of specific kernel in runtime, yeah, that was an overkill. So you can use this switch, a bit obscure but fully supported by one API, to tell the runtime that only kernels that are needed now should be compiled. You shouldn't compile all the kernels available. And yes, compared to OpenCL and CUDA, SYCL is not as mature and stable, which is good because you get nice new features and you can even influence the development of the standard. But it also means that sometimes things get deprecated, they get removed. Usually, in our case, all the removals were limited to vendor extensions becoming parts of the standard, so it was trivial to fix. But still, it means that if you have code working with, say, one API 2021.3, it will not necessarily work half a year later with a new version of one API because functions were renamed. And sometimes, yes, with any new technology that's getting a lot of features incoming, things occasionally get broken, so keep that in mind. It's not too bad, but it happens occasionally. So overall, the project started in September 2020 with initial goal of targeting Intel GPUs. And in January 2021, we already released the first version of GROMACS with some support for offloading non-bonded kernels to Intel GPUs. Then we started also exploring portability, and by September 2021, we made a decision to use SYCL as a main vehicle for future high-performance AMD GPU support. And now, in the coming days, we'll have a GROMACS 2022 release, where SYCL will be a fully fledged GPU backend comparable to CUDA and OpenCL. It is still marked as experimental because, yeah, CUDA and OpenCL had many years of testing in the wild, while SQL, for SQL, is the first year as a fully fledged first-class backend, but still we expect it to be stable enough. Yeah, here with more details. First, we only had one for potential ported and only supported GPC++ and Intel GPUs. And a year later, we have supported all three major vendors and SQL backends and have most of the interesting and compute-intensive forces ported. And actually now, SQL even have more features than our OpenCL port. So it is able to squeeze even more out of the hardware, to offload even more computation to GPUs also. It's still lagging behind our NVIDIA support. So in conclusion, the promise of SQL as a portability framework where you can run single code everywhere, it works. It's not perfect, and you still need to do some tuning, but only trivial changes are needed to get support for all three major GPU vendors with the same code. Of course, if you want to get a really good performance, you still need to do some vendor-specific optimizations here and there to specialize your kernels for different hardware, probably different generations of hardware from the same vendor. There's no getting away from it, but simple kernels, and if work well without any specialization, and if you're not interested in pushing the hardware to its limits, yeah, you can use the same code. It will likely work decently well. And besides, as with any new technologies, sometimes it doesn't work as expected. We are occasionally getting performance regressions, but with one API, we easily got performance comparable when using OpenCL backend, and when using level 0 backend, we actually outperformed a bit OpenCL. And yeah, good thing is that if you have OpenCL support, then adding SQL is usually trivial and doesn't require re-architecting your application. With CUDA, there might be some functionality that's expressed very differently in CUDA and SQL, so it might be less trivial if you want to have a nice code structure. And yeah, ecosystem is rapidly evolving, so if you write your code now, chances are you will have to do some maintenance to make sure it works a few years in the future. So it's not like you can write it and forget. It will require some care. To conclude, I would like to thank Intel Corporation for inviting me to this talk and for awarding me scholarship to do this work in GROMACS team. I would like to thank Heinrich and Roland from Intel for their help with all things Intel, and Axel from Heidelberg for his help with all things HipSQL. And of course, I would like to thank the rest of the GROMACS team, in particular Mark, Paul, Zillard, and Artem, for their collaboration and expertise. If you want to learn more, you can visit our website, look at our mailing list, or look at our GitLab, where we are doing all the development. Here's a link to our manual for the release candidate, and a paper that describes a bit in more details the algorithms we use for GPU offload. And if you have any questions, feel free to reach out to me. Okay, that's it, and I see there are some questions in chat.